Hi, it's Paul. Here's some R scripts to back up the content of the 3 proofs of the week for week 4, which involve Poisson distributions. Of course, these don't really add anything. They just show the results that are proved to be true in general. And the first of these is that the limit of a binomial distribution is a Poisson distribution. That is, the way you make a Poisson distribution is you start with a binomial distribution, make the number of trials n larger and larger, the probability p of success being smaller and smaller in such a way that their product, which we call lambda, stays constant. So let's pick lambda equals 5 and try this out. First we'll do a plot where we show absolutely nothing. We just set the limits on x and y, and type equals n shows that we're plotting nothing at all. So we've got a nice empty plot on which we can add things. Now points is a low-level function, so we can keep calling this, and the first case for which I'm going to call it is the probability of getting 0 through 15 successes if you have 25 trials, each with a probability of 20% of success. That certainly gives you an expectation of 5. By using type L, I get a broken line plot of this, and there it is shown in green. Now let's try the same thing. 50 trials, each with a probability of 10% of success. Again, an expected number of 5 successes. There it's plotted in magenta. It's fairly similar, but not exactly the same. We go to 100 trials, each with a 5% probability of success. Plot it in blue. 200 trials with a 2.5% probability success. It's now really looking as though these graphs are approaching a limit, and the limit is the probability density function for the Poisson distribution with parameter 5. So that's a nice way of showing that the limit of a binomial distribution with fixed expectation really is a Poisson distribution. Another thing that's proved is that the expectation and variance of a Poisson distribution are both equal to the parameter lambda. That's dead easy to do. The first moment is obtained by summing over 0 through 30. 0 through 30 times the Poisson distribution density function for a value lambda. I've chosen lambda equal to 5. And when I take probability times value and sum it up, I get exactly 5. To get the second moment, I square the value 0 through 30 and multiply by the Poisson distribution density function. I get 30, but that's not the variance. The variance is the second moment minus the square of the first moment, and it comes out equal to 5, which was proved to be true in general. Finally, let's look at the sum of 2 Poisson distributions. Let's do one with parameter lambda equals 5, another with lambda equals 2. And we can calculate for each of them the probability of getting a value of the sum from 0 to 15. The probability of getting something bigger than 15 is so small we can approximate it by 0. Let's make a numeric array to hold the probability for each of these. And then going from 1 through 15, what I will do is take the sum of the probability of getting a certain value from a Poisson distribution with parameter 5 and multiplying that by the probability of getting the corresponding value going from I down to 0 from a Poisson distribution with parameter 2. Notice that when you add something in 0 up through I to something in I down through 0, you always get I. So this sum is precisely the probability of getting a sum of I for the two random variables. Now we've got this. Make an empty plot. Plot the value for 1 through 15. What's proved in one of the proofs of the week is that the result is a Poisson distribution whose parameter is 5 plus 2, or 7. We plot that in a different color. We get perfect agreement, and that ends this script. That was quick.